Hi students, today we're continuing our modeling with periodic functions. So our first example is a classic Ferris wheel example, okay? You're going to get lots of Ferris wheel examples because it's a really easy way to picture sinusoidal or repeating motion, okay, periodic motion. So let's draw a little picture of what, so here's the ground. Here's my really bad Ferris wheel. Okay, it doesn't touch the ground. There's a little bit of space between it and the ground. Pretty awesome, I know. So a Ferris wheel is 1 meter above the ground. So here's your 1 meter. Okay? And has a diameter of 20 meters. So is 20. Okay? A rider completes 1 revolution in 1 minute. Okay, 1 revolution in 1 minute. So 1 okay. Model the height of a rider over time using a sinusoidal function. So step 1 is to draw a well-labeled diagram, which I did there. Well, so I'm going to label a bit more in a minute. And then convert this to a sinusoidal curve. So think about it. We're going to need to know the halfway point because that's the axis. So you can draw that here. And then from the middle to the top is 10. So you got to think about, why do we need to know the distance between the middle and the top? Amplitude, right? Now, where does this fall though? So this is 1 meter high, and then you go up 10. So this distance here is 11 meters to get to here. So what does that matter? Well, that's the axis, right? Here, I can show it here too. I'm not sure if you can see that. So it's 11 meters because this is 1 meter and then another 10, or the radius length, to get up to the middle. So we're going to turn this into a sinusoidal curve. Now, it doesn't say anything about where the rider is starting, so we're going to assume that the rider is getting on at the bottom and starting here. Okay, and they're going to go in this direction around the Ferris wheel. So you can draw just kind of a rough sketch here. So we need 60 seconds or 1 minute. It doesn't make sense to just label a minute. It makes more sense to put this into seconds. So this is going to be time in seconds, and this is height in meters. Okay, so then 30, so this is 15, and this is 45. Why am I doing 4 sections? Well, to represent the 4 quadrants of the circle, okay? So we start at 1 meter above the ground, and our maximum is going to be 21, right? Because this is 1 plus another 20, so that's 21 to get to the top. All right? So we start here, and after a minute we're back there, and halfway through we're at the top. Right? So basically go up like this and down like this. All right, so determine the key features within this context. So let's take a look at this. So our period is, we're going to use seconds, so 60 seconds. So therefore our K value is going to be 360 over 60, which is 6. Okay. Our axis. Okay, so that's halfway between our max and our min. So our max is 21 meters, and our min is 1 meter. Okay, because they never are 0 meters off the ground. They start at 1 meter. So that's divided by 2. So that's 11 meters. Okay, which is what we drew here. So our axis is 11 meters. So therefore, C equals 11, okay? So our axis here is when the height is equal to 11, but the parameter C is equal to 11 in the equation. So now we come up with the amplitude. We can tell just by looking at it that it's 10, or you can do, your max of 21 minus 11 to get 10, but this distance here is 10, right? Or this distance here is 10. All right? So now we have to think about a phase shift. So this starts at a minimum. So that's the assumption that we made. Okay, when it says include any assumptions, this is our assumption. Okay, so therefore we're going to use negative cos, and so therefore there's no phase shift. Okay, remember we always try to avoid a phase shift if possible. So if it starts at a min, don't shift it and use sine to shift to here. Just use negative cos. That's the easiest thing. Okay, so our A value is 10, our C value is 11, our K value is 6. We're using negative cos, so we can go on to step 3, which is creating a function. Okay, so we need to identify our variables. So let h at t represent height above ground at t seconds. Okay, we've converted it to seconds. So it's h at t equals our a value, or sorry, it's negative because we're using negative cos. So negative 10 cos, our k value is 6. We have no shift, so it's just 60 plus 11. So there is our function. Okay? We're going to test our equation. So test h at 0, test h at 15, okay, test h at 30. You'll see it works. You'll get 1 here, you'll get 11 here, which is what you should get based on your graph, and you'll get, 21 here at the maximum. So right after 30 seconds, it should be at the maximum of 21. So take the time to actually plug these t values into the function and make sure you're getting these values out, because you should. If you're not, either your calculator's in radians instead of degrees, so check for that, or you're entering it improperly, which means you absolutely have to make sure you see me so we can fix that. So using your model, determine when the rider is 4 meters above the ground within the first revolution. I mean, well, if you think back, I mean, you can see a graph up there, but I don't have it to refer to, so, it's only that. So the graph basically looks like this. We're starting at the bottom and we're going to the top, okay, where this is 60 seconds and this is 30. So if you think about 4 meters, that's about here. So we're going to hit 4 meters once on the way up within the first 15 seconds and once on the way down within the last 15 seconds. Okay, so we know that our t value should be between 0 and 15 and 45 and 60. So we set our function minus 10 cos of 6t plus 11 equal to, 4 to 4 meters, and this is what we have to solve. Okay? So remember, to solve this, we need to get it in the form of cos with the argument equaling just a number. So we move the 11 over. 4 minus 11 is negative 7. Okay, so minus 10 cos of 6t equals minus 7. And then we divide both sides by 10. So cos of 6t equals 0.7. Okay? And now we need to include the range. So it said within the first revolution, so that's between 0 and 60 seconds. So now we change this, we let u be equal to 6t. Okay, this should be a review at this point. So because we're multiplying t by 6, we have to multiply this by 6, 360, and 0. Makes sense that it's between 0 and 360 because it says 1 revolution. Okay? So then you're trying to solve cos u equals 0.7, where u is between 0 and 360. So take a break, try to solve this on your own, because you have done this in the past, so you should be able to do this. Okay, so then you just go back to the Cartesian plane. Cos is positive in this quadrant and in this quadrant. So you have u1 and u2, and they both share the same beta. So you find beta by doing the inverse cos of 0.7. You find out that beta is 45.6. So therefore your u1 is just 45.6. and your U2 is 360 minus beta, so that gives you 314.4 degrees. Okay, so now you have the answers in degrees. You need to change them back to time by setting the U values back to 6t and solving for t. So when you do that, you get T1 equals 7.6 seconds and T2 equals 52.4 seconds. Again, you're just setting each of the U values, so the 45.6 equal to 6t, and then dividing by 6 to solve for t. So then you write a nice little sentence saying the rider is 4 meters above the ground after 7.6 seconds and 52.4 seconds within the first revolution. Okay, so that's our first extended example, I guess, for today. We have 2 more. By all means, I would encourage you to try them on your own as much as possible. See how much you can get. Okay. Now this next example involves a Ferris wheel again. Okay. But it gives us kind of a different set of information. So a group of friends is tracking a friend on a Ferris wheel because, you know, they have nothing else better to do. They know that John reaches the maximum height of 11 at 10 seconds. So I'm going to break this out, this information. So here's the Ferris wheel. I'm assuming it's not right on the ground. And this is a shorter Ferris wheel because its maximum height is 11 meters. And its minimum height is 1 meter. So this happens at 10 seconds. And this is happening at 55 seconds. Okay. Develop the equation of the sinusoidal function that models John's height above the ground to determine his height at 78 seconds. And also then when he is 9 meters above the ground in 1 revolution. So basically we need to come up with the equation first and then answer a couple questions about it. So the black drawing here represents the exact, I'm just making sure you can see that. Let's just shift this a bit. Okay. So that represents the exact information we were given. And then I'm going to draw in pink to show you kind of what I'm filling in and inferring. So I need to know the halfway point here because that's the axis. Okay, so if it's 1 meters to 11 meters, this whole distance then is 10. So that means that this smaller distance here is 5. And this here is 5. Okay? So that means my amplitude is equal to 5. You guys get that? Okay? And that also means that the axis is 1 plus the 5. So my axis is equal to 6. So my C value is equal to 6. Now, in terms of the period, from a max down to a min was 10 to 55 seconds. So that was 55 minus 10, so that therefore 45 seconds. So that's only half of 1 revolution though, because in an incomplete revolution you go from a max back to a max. So in reality, the period then is equal to 2 times 45, so 90 seconds. So it takes 90 seconds to go around the Ferris wheel once. So let's create kind of a little sketch of what's going on here. So we're going up to 55 seconds. So let's go 10, 20, 30, 40, 50, 60 seconds, okay? And let's do 5 and 10. This is for height, this is time. Okay, so at 10 seconds he was 11 meters high, so at the max. And at 55 seconds he was just 1 meter high. So this is all we really know. So we would assume he was here before and then is going up after. Okay? So now we want to actually come up with the equation. So we don't know if at 0, if he was actually on the axis. So we don't want to infer information. We want to use the most solid information we have. So we have a solid information that our maximum happens at 10 seconds. So we're going to use a cosine function because we know the maximum. And we're going to shift it 10 to the right because that's where the maximum occurs. So we can show this visually here if you are a visual learner. So the original cos has been shifted 10 to the right. And we're going to use cos because we're starting at a max. So therefore, our function then, you say you represent your variables. Okay, it can be the exact same as we did for the last question. H at t equals our a value of 5, cos, because I'm using positive cos, bracket. My k value is, where's my k value? Oh, I haven't found my k value yet. So my k value is 360 divided by 90. So that is 4. Okay, so 4, bracket, t minus 10, bracket, plus 6. Okay, don't forget you have to show the k factored out in order to show the phase shift properly. Okay, so this is our function. Check it over again. We use cos because we're using the maximum as a starting point. We have a phase shift of going right 10 because to get the maximum at 10, the original cos would have had to move to the right 10 units. Okay, our k value is 4. 360 divided by 4 is 90. That's our period, so we did that right. My amplitude is 5. So from the middle, the axis to the top is 5 meters. And my axis is 6. So from the ground to the middle is 6 meters because it's the 1 meter plus the 5. So I'm satisfied with that. Okay, so now I want to solve these problems. The first one is what's his height at 78 seconds. So that's just literally finding h at 78. So you're just putting 78 into the function. So when you do this, it's in here, right? So you got to do 78 minus 10, 68. 68 times 4. So you find the cos of whatever 68 times 4 is. Then you multiply by 5, and then you add 6. So you have to follow BEDMAS. Do the argument first, the cos of that argument, and then complete your equation. So when you do this, you get h at 78 is 6.17 meters. Okay? The more complicated question is solving the other part. When is he 9 meters above the ground in 1 revolution? So that's answering the question, solving h at t equals 9 in 1 revolution. So basically between 0 and 90, okay, because 90 seconds is how long it takes to complete 1 revolution. Okay? Now, you can make a case for doing between 10 and 100. That would also make sense because we're doing from a max to a max. But again, it has to be, because it's 1 revolution, your 2 t values have to be 90 apart to show 1 revolution. So I'm actually going to let you guys do that question on your own. I want you to do it on your own. You should get t is equal to 23.25 seconds, and t is equal to 86.75 seconds. So I want you to try that on your own because it's the exact same method we just did in example 4, so you should be able to figure that out. If not, we'll work on it in class. But try your hardest, okay? This is a really crucial part of the unit, and you will have this exact stuff again next year in grade 12, advanced functions. Okay, one last example, and it's not a Ferris wheel. It is a flagpole flapping back and forth in high winds. So let's picture what this looks like here. We have the ground, and we have a flagpole, okay, which normally goes straight up. Now, it can go 10 centimeters to the right. Okay, this is 10 centimeters. Obviously, this is an exaggerated picture because that's way bigger than 10 centimeters. Flagpole would never go that, like, wah, wah, wah. It's just going, burp, 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 but I kind of exaggerated what it looks like. So it's going 10 that way and 10 the other way. So it does that 240 times every minute. And it starts at its resting position. So we want to come up with an equation for this. Okay, so first let's show this on a graph. Okay, so we're assuming that, let's assume that this is time, and this is F at t, okay, so it's flagpole at time, and let's assume that its resting position is just 0, so zero sway. Okay, so it's going to go up to a maximum of 10 in the positive direction and down to a minimum of negative 10 in the other direction. So we'll say right is positive and left is negative. Okay, that is an extremely, that's what we use in physics and vectors. Right is positive and left is negative. So it said that it started at its resting position and moved to the right. So we also know that this does this 240 times every minute. So 240 times every 60 seconds. So that means it goes 4 times every second. Okay? 240 divided by 60 is 4. So 4 times a second. So therefore, 0.25 seconds is 1 period. Right? Because it's a 4 times a second, that means a quarter of a second is a period. So 0.25 we can put, and 0.5, I'm going to show 2 cycles. So here's halfway, halfway, do. Okay? So it starts there, it goes to the right. It's going to move back to its resting position, to the left, and then back to its resting position. Back to the right, then to the left, resting, then further to the left, then back to resting. Okay, so it models a very clear sinusoidal curve. Okay, especially if you draw it properly. Okay, there you go. Kind of rough, but that looks really rough. What's that? Okay. All right, so let's come up with our equation by looking at the key features. So our axis is just 0, okay? Our amplitude is 10, okay? Our period, we found out there is 0.25. So therefore, K is equal to 360 divided by 0.25, which gives us 1,440 as a K value. We start at the axis, so we're going to use positive sign with no fascia. Yay! Okay, so our function then will say let f at t